Neutrinos are tiny fundamental particles that are all around us, but we fail to notice them because they almost never interact well with anything. However, their unwillingness to interact with matter makes them perfect spies. Even photons that are produced in the core of the sun take around 100,000 years to reach the external sun layer, but neutrinos easily penetrate solar plasma and they are on their way to the Earth. In 2020, with the Borexino experiment, we saw the first experimental evidence of neutrinos originating in the CNO fusion cycle in the sun. CNO stands for carbon, nitrogen, and oxygen cycle of proton-proton fusion into helium. It contributes about 1% of total energy of the sun, but there are several reasons why this 1% is such a big deal. First of all, this is the first experimental evidence of this mechanism of stellar energy production, even if it was hypothesized back in late 30s of 20th century. Second, CNO cycle is expected to be dominant in stars heavier than the sun, and this is a very large number of stars. And their rapid evolution makes the CNO the primary mechanism of stellar conversion of hydrogen into helium in the universe. Finally, the most pressing question in solar physics is the so-called metallicity problem, the fact that spectroscopic and helioseismological measurements of the chemical composition of the sun do not agree. Metallicity influences also neutrino fluxes, and our super spy CNO neutrinos are the most sensitive to the sun's core chemical composition. The same property that makes neutrinos so ideal to getting information from the core of the sun also makes them particularly difficult to capture here on Earth. This is why neutrino experiments are usually rather big. The active volume of the Borexino experiment is around 300 tons, and it is located at Laboratori Nazionale del Gran Sasso in Italy. The mountain above the lab provides 3,800-meter water equivalent shielding that reduces cosmogenic background by a millionfold. Moreover, the inner part of the Borexino detector is extremely pure, 10 orders of magnitude less radioactive than air around you or ordinary drinking water. This level of radio purity was not obtained by any other experiment. In addition, the whole detector was thermally insulated in the latest years to better understand and control the remaining backgrounds. Discovery of neutrinos originating in CNO fusion cycle was a complicated task that required a great deal of effort in both hardware and software from many people of the Borexino collaboration.